Welcome to the CANA Connection podcast, the podcast where all things analytics, logistics, operations, and whatnot we talk about. So on today's podcast, we are going to be going over some interesting things about a project, a program called Mimic, and other things. I am going to hand this on over to Jack Murray. Jack, go ahead and introduce yourself, and then everybody else, take it away.
Awesome. Thank you, Koa. Yeah, my name is Jack Murray. I'm a project manager here at CANA. I work with the gentleman on this call for multiple projects here in the energy and unmanned systems realm. Like Koa mentioned, we are going to start with some introductions and then really get into the topic of conversation today, which is metamaterials, their role in small unmanned aerial systems, and it really in the Department of War, and how we here at CANA are addressing a critical gap in this arena. Chris, I'll pass it over to you first to introduce, and then Eric.
Hey, thanks, Jack. Good morning. I'm Chris Cichy. I'm the Director of Innovation and Strategy at CANA. Prior to coming to CANA, I was the CIO for AI and autonomous systems at the Marine Corps, and a lot of what we're going to talk about today is kind of a follow-on from some of the work that I started while still on active duty.
Awesome. Thank you, Chris. Eric.
Hey, my name is Eric Goumillout. I'm the Senior Electrical Engineer here at CANA. Been working on some fun projects related to energy, and in the past I worked on electronic warfare systems and design and process engineering.
Awesome. Yeah, there's a lot of technical words in here, and I know I mentioned one of those being metamaterials, and that's going to be a topic of conversation today. So let's start off by just Eric walking everybody through what metamaterials are.
So metamaterials are basically a composite material. Composite meaning there's multiple materials inside of it. Typically it's based off of a polymer like PTFE, and within that design and within that material are electronic pathways that have been designed into it. So there's many ways of doing that. You can 3D print electronics pathways in that material. You can do like ink screening on multiple layers, but generally the thought is you are adding characteristics to material that normally wouldn't have those characteristics. In this case, electronic characteristics that you have modeled ahead of time to do a specific task. That could be gathering energy, redirecting energy, absorbing energy. But basically you're adding all these really cool material effects to something that normally has none of those. And that's a gist of what metamaterials are.
Awesome. Chris, anything to add to that? Or
Yeah, I think what's exciting about the metamaterials that we're working with here are their abilities to impact radio frequency or RF. We'll get into the operational use case, I'm sure, in a little bit here, but essentially what Eric's describing is being able to redirect, to absorb, to reflect, completely reflect back at an emitter, different kinds of radio frequency, all the way up to, photo optics, lasers, in a sense, are also, RF energy.
Awesome.
Or I should say electromagnetic energy.
Yeah. Well, I mean, we noted that they have that role in Department of War's unmanned aerial systems, and you already brought up some of the use cases we'll get into. So we can just start by giving the problem background here. What's that gap right now facing the Department of War in the UAS arena?
Yeah, it's not as simple as like one major gap, because like anytime you come up with a solution to a capability gap, you open up new gaps, right? So
Yeah.
I brought this one thing to solve the problem that you had, and I created 3 more problems based off that solution, right? So the capability gaps are multiple, but in the case of the unmanned systems, some of this is taking lessons learned off what they were seeing with the use of unmanned systems in the Ukraine versus Russia. And in that particular conflict, a lot of military unmanned systems were being funneled over to the Ukraine, and then obviously the Russians were using their own. And then to keep up with the pace, the Ukrainians in particular were purchasing a lot of commercial off-the-shelf drones, doing some kind of cowboy engineering and retrofitting them and making them military capable rapidly. What they initially found was that the the level of training you had to have to get their soldiers up to speed on these military UAS was pretty high. They started developing a preference for the commercial solutions because they were way more intuitive for their, untrained, it's not their specific job. So that kind of untrained operator to be able to rapidly field and use in combat. But with that, this move towards these rapidly acquired commercial systems, that opened up these other capability gaps that I think are pertinent to this, in that one of the major differences between a commercial drone that you would say buy off Amazon and a military purpose-built drone is their level of RF hardening. So, the Russians obviously had some ability to do electronic warfare, and they were initially jamming a lot of these drones, either jamming the control or jamming the position, navigation, and timing, essentially the GPS of the drone. So if the drone doesn't know where it is, it's hard to control unless it's a first-person, an FPV type drone. So with that, you saw two pushes. You saw a push towards FPV drones being used. Obviously, those are limited by line of sight. And then you started seeing a push towards these fiber optic wire guided drones. So where there was a wire actually connected to the drone that would spool out and control the drone. Those have their own limitations. They're affected by, obviously they get snagged in terrain. If one of those hits water, it fries the drone and can fry the operator. So they had their own limitations. What we're able to do with the Metamaterials Eric's talking to, we'd put together a project called Mimic. In that project, the idea was we would take some of these metamaterials that we were developing with our partners to either absorb the RF energy, thereby protecting the drone from jamming, to be able to maybe redirect it. So in the case of high power microwave, we could either dampen a high power microwave weapon down to the point where it's not hurting our drone, or simply redirect it back at whoever's broadcasting that high power microwave. So, zapping the zapper, if you will. We can redirect it around. So we have done several projects with wireless power transmission, and in those projects, a lot of times what we were focusing on was directing it all and focusing it onto the center of several lobes of a rectenna. In this case, you could take that same rectenna with several different lobes on it, if you will, and direct individual components of it so that there was the maximum amount of beam on each lobe. And what that would allow you to do is take some of that RF energy that was being emitted, convert it to power, and extend the range of your drone. So we're solving several different problems all at once. Eric, you have anything to add on that?
Well, one of the interesting things about using metamaterials is it allows you to have the protections on slower group 1 to 3 UASs that you normally have on the group 4, 5, and 6, just because with the smaller drones, you don't have as much of a threshold for weight, because weight at that size is critical, and it will definitely impact how the airframe behaves. So you can't overcome that with thrust on like some of these larger UASs. So being able to integrate a metamaterial into the aircraft or the platform allows you to maintain your same performance characteristics without, and same performance characteristics and adding the hardening, with no sacrifice, which is pretty sweet.
Yeah, and I think that gets into the value proposition. I mean, everything that Eric and I just described, there's already materials and components and systems out there that do this. The big differentiator is, one, our swap is really small. Two, we can additively manufacture everything that we're discussing. So we can tailor it to an environment out on the forward edge. As far forward as you want to push a very common off-the-shelf commercial, 3D printer, we can print components for these unmanned systems that give it capability that normally would require, very purposeful building in a factory setting with, regular traditional manufacturing. And third is cost. The materials we're talking about are not exquisite materials. I think, maybe our most expensive material right now is something like $60 per kilogram. And that's just one component of that, what would you call it? Layered polymer that they're making for the metamaterial. Compared to something like a Faraday cage or, the exquisite paints that they put on, say a stealth aircraft. We can harden against RF. We can have stealth-like capabilities. We can redirect different kinds of RF signals for different purposes. And then underneath that, this metamaterial also enables a plethora of other capabilities related to power transmission, related to things like geolocation of RF emissions. So essentially, you can take the metamaterial, a 3D printed rectifying antenna, phased array one, and you could tell where everything was emitting and maybe even beam write it down. So you could turn commercial off-the-shelf drones into mini harm missiles, on the cheap.
No, it's really interesting. I mean, it sounds like you guys talked through some of the current solutions out there already, but I mean, we internally feel like the work we're doing here is very innovative, right? Compared to the current solutions out there, do we see anything that is, currently trying to solve all these issues at the same time, essentially, that Mimic is doing, and then also having that cost benefit of really solving the issue up front and making it kind of a easy, cost effective, repeatable process? Or is Mimic right now, would you say, an early adopter in this phase?
I would say it's on the leading edge. I don't know if you've seen anything else, Eric. Everything that we've discussed right now has been kind of proven out in the lab. We have published research to back all this up. What we're really hoping to do is get that next phase out into the operational environment. Some of the supporting capabilities we discussed, like the wireless power transmission, like the ability to detect RF and either do kind of signals intelligence, collection, gathering, and mapping of that RF, or no kidding, like geolocation and potentially beam writing down to that to strike it. Those are things where different components of the technology have already been proven out. What we're doing is doing it on the cheap at a very low swap, and being able to tailor it on the fly through the additive manufacturing process. So, there's other people kind of doing it, but just not in the same way, and definitely not with the value proposition that these projects would bring.
Yeah, a lot of the utilization of metamaterials right now is with like satellite communication systems. So it's just purely adaptive communications and not these other unique approaches. And that's what's cool too with it being such a rapidly deployable thing, is you can map out your energy that you might anticipate experiencing in the field and print a component that has been already mathematically designed to interact in that environment ideally. And you can in any environment, you can adapt it to what you expect to experience in that environment, which is really cool.
And if you think about a conflict, kind of like a steady state conflict, like the Ukraine conflict going on right now, the longer a war stretches out in general, and taking, current technology out of this, throughout the history of warfare, it's a constant competition to evolve, and whoever's technology kind of evolves, tactics evolve faster, typically wins, right? So you were looking at, Russia came in with overwhelming military force. We fielded a bunch of specific technologies and allowed little Ukraine to kind of, hold them off. The Russians then countered with, a giant increase in electronic warfare capabilities on the front. They then started flooding the zone with first-person, FPV type drones and wire-guided type drones, and this kind of back and forth of technology is going. So being able to, rapidly adapt through additive manufacturing at the point of friction is something. Just as a concept, take what we're doing with it in the metamaterials out of it, but that concept of being able to manufacture capability at the kind of point of impact, that's what helps win wars. That's what helps win conflicts like that, and enables that rapid adoption of technology. So often we wait as a Department of War to field technologies till they're perfect, and by the time they're perfect, and we're not wasting any taxpayer money because everything, works on it, the technology is old. And that's another knock against these military systems that we were fielding to, say the Ukraine and other partners. By the time we get something all the way through the acquisition system and then through the foreign military sales system, and we get it out to them, they can buy something off Temu that's better, has additional capability. Shoot, I saw a Chinese electric vehicle the other day that has its own drone. So when it gets stuck in traffic, the sensor detects that there's a traffic jam, auto launches the drone. The drone goes in and takes off, broadcasts full streaming video to the center console of the car, right? Tells them where the traffic is and suggests reroutes, and then automatically lands back in their car. And this is a commercial product. Meanwhile, we can't field a semi-capable drone to our armed forces.
Yeah, I mean, well, you touched on really the warfighter value and then why we need to move rapidly, right? But you also mentioned the stage we're currently at with our solution here, Project Mimic, and getting to that next step. What was that next step for Mimic?
It's really operational testing. I mean, we've tested these materials in the lab. There's zero reason that they shouldn't work. Yeah. The things that we need to test are, the ability to, if we're talking retrofit, not creating OEM parts, because creating OEM parts is something we definitely do. If you're a drone manufacturer and you just want us to make you the components, we could do that. But if you're the DoD and you've purchased these commercial drones where, you got this drone at the cheap, but say you want it RF hardened, against these kind of frequencies, we would scan the drone, print the components, snap them together, and now you've got that. It's testing that whole manufacturing process. Right now, the surfaces that we're working with are conformal. We want some ideas of durability. I mean, long-term durability isn't necessarily the point of this, but we still want kind of those metrics, how it works with vibration, how it works with heat, how it works with cold up at altitude. Like these sorts of testing metrics that we can't really get in the lab. Those are really the next step. And it could be down to those little things, like depending again on how the government wants to employ it. Like if their desire is for, parts and we just create capabilities for other OEMs to strap onto their drones, that's one thing. But if they want the ability for soldiers, airmen, whoever to be able to, as I'm going into an area, the intelligence assessment says this is the specific RF threats, this is the RF environment in that area. We want to make these drones stealth, right? And they need to be this frequency of X-band radar, right? Yeah. Then the person in the field goes into the 3D printer, plugs some things into the model, and prints out the components for the type model series drone that he selected, right? And then once those are printed, we disassemble, assemble, snap those components on, and away they go on the mission. Some of that would take some validation as far as the process, developing maybe the software UI that would allow them, a non-engineer person in camouflage uniform to go in, select everything he needs to select, and let the model spit out the design that he wants. Most of this, the mathematics is already there. They're doing it with different kinds of engineering software, but that's not the type of intuitive thing that you would want the Lance Corporal to use. So building that interface to the software, if the expeditionary manufacturing capability is something that they're interested in.
Yeah, I was actually going to bring up the whole stealth piece. I know we've been talking about what it can currently do and the value it currently has, but going into what it can turn into if we continue to develop out and test use cases is truly amazing to hear just internally when we discuss it. So I'm glad we're talking about it for everybody else to hear. My question, two questions that come to mind while we were talking. One is, does this require, once it's, it's tested, it's operational ready, and we have it ready for use, is there any training that goes with this, or is this, just a super, you give it to them and they can plug everything in and it pops out the answer?
If it's just parts, it's passive, right? So if we put the parts on your unmanned system, it's passive. You don't have to do anything. If you desire to manufacture themselves, there's probably some training involved, and what we would provide would be a software and a process, right? Here's the recipes, here's the software, plug your stuff in, these are all the materials you needed, print your parts, and this is how you would go ahead and assemble them.
Yeah, but fairly easy, I would
fairly
assume.
easy. Yeah.
Fairly easy to understand, even if you're not the technical SME, like I would be able to do it. So, no, that's super. That's super cool. I mean, I know we've talked a lot about this a lot, but if you guys could give, 1 to 2 sentences about why people should really care about this? What's the largest, value add that, our work here with Project Mimic, offers the DOW and others?
I think it enables the rapid adoption of other capabilities. So, nothing says these, and I've used UAS as an example for a lot, but RF hardening, stealth, the absorption of radar, and lowering your radar cross section, the ability to reflect different kinds of electromagnetic energy away from whatever, yourself, right up to the, different systems. This kind of applies across the board. So it's an enabler that allows for the rapid adoption of technologies that aren't ready, right? So you see an unmanned ground vehicle and, you're an acquisition officer. I'd love that thing, but, it lacks these capabilities. It lacks this survivability characteristic. This is something that you can pair with that and give it the survivability characteristic that you desire as a military system, and get it out into the warfighter's hands exponentially faster. And again, there's the no kidding physical cost. It's just going to be cheaper.
Yeah, that's where a lot of attention goes, right?
Yeah,
is the cost.
Faster, cheaper. And
we could talk about how great it can be, but most of the first thing people want to look at is usually how much is that going to cost. So, no, that's a great explanation, Eric. Anything to add to that, or?
Well, what gets me most excited about it is just how adaptable it is, and you can approach almost any RF electronic warfare situation and have a solution quickly. And if you don't have the proper model on hand, you can basically phone home and have someone model it and digitally upload it to you, and you can immediately print it out. That's so cool. And that to me is the best part, is being able to be adaptable and help the warfighter be more effective.
I mean, yeah.
A lot of our work with this technology, we've been able to spin new prototypes up in a matter of weeks. Like our biggest limitation that's driving us to, or our biggest constraint that's driving us to those weeks, is usually like external components to connect it, to actually integrate it into gear. Diodes and whatnot that we would want to solder onto it to attach it to something else. So as long as your supply chain of integration is there, the little electronic components that allow you to connect it to the power supply of a system, say, it's as fast as you can get into the modeling software, get your new design, and then hit print,
Yeah. No, I mean, from my point of view as well, like I've said throughout my non-technical, helping a little bit with this project internally and hearing this podcast is just super exciting to listen to, especially with, how much emphasis and priority is being put on the main example that we've used throughout with the unmanned systems. Now, I think I only have one question left as this conversation was going on, and it kind of goes back to something else here at CANA we're working on, something called Entourage. Which we've talked about before. If you're interested, you can visit our website, canallc.com. Chris, really a question for you. We talked about why people should care. We've talked about, the value and all that, all the different differentiators. With regards to Entourage, we're looking at that as, it can help at the strategic, tactical, and operational level. Is this the same with Mimic? It can help at all three levels, or is it mainly an operational?
I would say it's probably... It has application across all three levels of war.
Okay.
I would say this is probably more an operational and tactical level capability. But if you start looking at it from a contested logistics lens, right? So, take Indo-PACOM. If I want components or systems in Indo-PACOM and they are coming from the States because they're blue and I need to make them here, I've got to transit the ocean either by sea or by air with those things to get them there. Or I've got to stand up the manufacturing capability in like that third or second island chain. Probably not the first. That wouldn't be a great idea. The thing with traditional manufacturing is it requires a lot of trained people. It requires an exquisite facility, typically, right? And that makes a juicy target. So if I strike one of those, your ability to reconstitute it is severely limited, especially if I take out trained personnel, because you don't create those overnight. Trained personnel take a lot of training plus experience to be good enough to do that particular job. where this can kind of get into a strategic enabler, if you will, is through the manufacturing process, right? I can stand up a factory, if you will, that is some mildly trained Marines who basically know how to turn the printer on and they know how to interface with this software, right? And I can put a couple of electronic or 3D printers with some raw materials, run it off a generator, and I've got a factory. And it's very mobile, right? But if you manage to strike my factory, granted, all the Marines' lives and all the soldiers' lives are very important, but it doesn't take as long to make more of them as it takes to make engineers that work in a traditional manufacturing facility. So I give it to the next group of Marines, I ship them another printer, they connect it back to another generator, and I've got a new factory. Knowing that the ability to reconstitute it is a lot more rapid, makes it much less likely that they're going to waste a missile on that target, right? When I'm looking for targets to strike, one of the things I look at is the criticality, but I also look at recuperability, how fast you can recoup that capability. And if you can turn it back on overnight, it drops way down the list of things I want to strike, right? So you're protecting your manufacturing base on one hand, and you're easing your strategic contested logistics problems on the other hand, if that makes sense. I know that was a little bit rambling.
No, I mean, it made sense to me. And there's just so many possibilities with this, right? Like you mentioned, it could help at all levels. Now, I appreciate both of you taking the time to talk through this today, answered all my questions, and I hope my questions were some of the similar ones that people out there had. And I guess I'll open it up to you guys one more time for any last comments or closing statements on Project Mimic or anything else that we discussed today.
You want to go first, Eric?
Like I said before, I'm just really excited about the technology and being able to be working at a company that allows me to interact with this technology, be on the cutting edge, and do so many cool things that are really useful for the warfighter and even in commercial residential potentially down the line.
Awesome. All right. I guess I'll just end with, hey, Project Mimic is one of a series of very cutting edge R&D projects that CANA is working on. We've had Project Mimic, which is working on that metamaterial that we've been describing. We've had Project Arson, which was looking at taking RF energy and turning these low cost attritable unmanned systems into replacements for $1.5 million HARM missiles. We've had Project Reaper, which was aiming on extending the endurance of very cheap unmanned systems. Yep. So you'll see the theme here is they're all additively manufactured. They're all very, very low cost alternatives to existing technology, and they give capability to the warfighter at a much more rapid rate. And they're all linked. If you can do one, you can do the other three. So we're really excited about the way this is going and trying to get some of this capability into the warfighter's hands.
No, that was very important. Thank you for that, Chris. Thank you, Chris and Eric. And we'll close out with that. Thank you all.
Yeah, excellent. Thank you very much, everybody. But guys, I have a random final question here that may or may not make it into the podcast episode or anything. We come up with weird names for things all the time, and sometimes we try to make acronyms and everything like that. I have a question. Is Mimic an acronym for anything, or is it just a cool name for the way it operates?
That is
an acronym, but I particularly like this one. Eric got this one. It was Metamaterial Integrated Manufacturing for Intelligent Chassis.
Wait, say that again?
Metamaterial Integrated Manufacturing for Intelligent Chassis.
Cool. Yeah, I was curious the whole time. I'm like, I'm a big gamer, right? So a Mimic is usually a chest or a wardrobe or something like that tries to eat the person trying to steal the goods from it. It's like,
I loved it because if you think about what we're doing, we're taking a COTS drone, at least in the project that we proposed. Obviously, we can do other things with technology, but you take a commercial drone you bought from Amazon, you scan it, you print new components, and you snap them back together, and now it's got all this additional capability.
Yeah, it's kind of brilliant. I love the concept. I want to see where we take it and everything. So that was today's CANA Connection podcast. Again, I'd like to thank Eric, Chris, and Jack for joining us today, and we're going to have them back. We're going to talk more about this kind of stuff. Follow on your favorite streaming platform for your podcasts or over on our YouTube channel. That being said, thank you for joining us. This was the CANA Connection podcast. Remember to analyze, assess, and execute, and we will catch you next time.